These teaching devices today. So we have started doing filtering last time around. And why I need my props here is just to explain the basic filtering using props. So just as a brief review, we need to filter images, often because of the noise that is inherent in the image. And we will go through a number of types of denoising, but this is something that is ever evolving field. Now, one key message is that filtering is information loss. Except that noise is the type of information you want to lose. Right? But if you don't have a lot of noise, do not filter. Right? So you do have to look at your image to make that decision. And this one, more likely than not, unless you do filter, if you don't do filtering, you're not going to move forward, essentially, in your analysis. Second point that I wanted to make, so we often look at the histograms as part of the information of how our image looks like. So basically, that's a statistical summary of our image. And we can immediately, if I'm looking for, if I know that I'm imaging a porous medium, I should see two phases in that image. And I can immediately, if I don't have clear distinction between the phases or the populations in the histogram, when I put them together, I have problems that I need to deal with. Okay? So in order to do that, we might need to do some filtering to actually make this better for further processing. Nothing really replaces higher resolution in getting a better quality image. Now, one thing that we also have to understand is that you don't have to necessarily filter, but you can just do basic manipulation of the image, which gets you off your regular grid that you were on, such as rotation by an angle that is not plus minus 90 degrees. And the moment you do that, and sometimes software does things for you without telling you, you might have information loss because of interpolation. So that's something to understand. Second source of information loss is possibly inherent changes to the type of the numbers you're using for grayscale. 16 bits to 8 bit, there will be a linear conversion there, and chopping off to be integer, to remain in integer world, and there's an information loss. So that's that's not necessarily filtering, but it's basically manipulation of the images. So the best way to understand filtering is through convolutions. Now we're normally used to one-dimensional convolution, where you might have a discrete signal, and then you have sort of like a Gaussian, where you basically convolve the two with a shift that basically that Gaussian is shifting through the entire real line. Then you will actually get a resulting sort of spread of that impulse as a result. And that's basically, you can think about it as a one discrete line that is convolved with a Gaussian, and that's how we often interpret signals. What it comes down to in 2D, and convolution is similar as a correlation of the image, is if I assume that this is an image in 2 dimensions. So now, right now, that is my 2-dimensional field on a grid, and I'm going to be very sort of discrete here with like only 4x4. And then if I'm trying to convolve this is of course not matching, but almost matching. So I'm going to pretend that this is, or maybe I should, there we go. It's going to be very, I need more, but I'm just going to pretend that this is a 2x2. So basically what I'm going to do, normally we don't do 2x2 filters necessarily, But what you do is you assume this second function that you're convolving with has a finite support on your grid. It's zero everywhere else. So what you will do is you will isolate yourself and center in a voxel and basically sum up, multiply whatever you have in your function f times g over that grid and sum it up. Okay? And then there's a result. And you're going to move over by 1 pixel and do the same and sum it up. And do the same and do the sum. Result of that convolution is another image. Now, often we can explain that we need to, for that operation, so this is a properly drawn with something that has a center in there. So if I'm doing it in the border voxels or pixels, I can't do this, right? So I have to pad an image to produce an image of the same size. And that's something that we always do with any kind of differential operations. If I wanted to express a derivative near the boundary, I'm missing the outside information, so I gotta assume some sort of a boundary condition. So often we can just copy these values here, or pad with a 0, and the boundary will look slightly different based on the assumptions we made. So essentially, this is called both correlation and convolution. I'm writing this shift as basically this summation and doing the integration over this small support is essentially summation. So instead of integral, now I have summation. And depending whether I have a plus and minus, I'm not very rigorous here. I will either call that cross correlation of two functions or a convolution. And this finite support sort of stencil over which I'm actually summing things is called my convolution kernel. Because everything else is a 0, so I just ignore everything else. But I can just assume that this function g is defined everywhere with this finite support over a stencil kernel. And how big that stencil is I define that. So is that clear conceptually? I'm waving my hands, but I want you to conceptually understand. So I'm not writing everything down very rigorously. All kinds of filtering and manipulations can be viewed in that same way. So that's why kind of like understanding convolutions is similar to basically formalizing mathematically what are you doing when filtering. So for instance, I can write down any kind of differential operator, always is on a fixed stencil around center with a point. Right? And basically how I'm combining nearby values, I could basically evaluate a differential operator in terms of central differencing, backward differencing. I could do the same using these stencils. And so that's a type of filtering operation as well. So you can basically link doing derivatives and all kinds of differential operators on an image with convolutions as well. Okay? So there's a stencil kernel that you can, and it has a finite support around the point. And you're just doing that in a digitized world. Okay? Now there's a good, and I'm going to update the files. As in the meantime, looking if there's a good sort of online video that explains that. And there's an excellent one. This is actually a course on cryo-SEM. So cryo-SEM is the frozen SEM used in biology a lot. Right? So basically manipulation of those images is still manipulation of images, whether they're biology or not. And when I grow up, I will teach this well. Okay, that's my joke. It's an excellent, Grant Jensen is an excellent teacher. And also the videos are done really well. So please don't judge my videos after you see these, but those were professionally processed. Okay, that's all I'm gonna say. So it's actually I found a particular video that I'm linking here that is just explaining convolutions and cross correlations. That I think it's a 10-minute or 10 and 15-minute video that you can watch. but it's actually a part of series. Okay? And you can also, we're not going to go into details on Fourier transforms, but basically Fourier transforms are used for a fast processing of this filter and are often running behind, basically making things that are making things process fast. Okay? All right. All right. So Gaussian smoothing is often viewed as removing a function that is like looking like this with some sort of support, compact support, and I just then project that on a discrete version of a filter. So this is how it would look like if I'm assuming that this is my compact support. Right? So I can see that this is basically a version of a circle in a 3x3 digital world. Okay? So basically this is how approximately something like a Gaussian kernel would look like. And you could balance all of these ones, and this could be, for instance, a 4. So what is the difference between this number and the surrounding numbers can be adjusted. Okay? What is your height of your Gaussian? So if I was convolving an image, I would basically, this would be something that I would slide around the image and basically get a result. And we have seen in our exercises, okay, that you can actually define. So there's, in process filters, you can see what is your support in form of a circular mask. And then you can, for various types of filters in 2D, you can actually define what the radius would be. So you can see what the support is and what the radius would be, or you can even define it yourself and then convolve with it. So you can play with that if you wish. Now, there was a quick in-class assignment. I claimed that the median filter is changing the image less than median filter, whatever that meant. Okay. So what were your conclusions? The same. I found in the meantime, so I was kind of shooting off the hip because this is what I've used and I've used in my own research. And I have typically used histograms to prove it to myself. So that's what I quickly assigned to the using the image that we had in class. Now, I was in the meantime thinking, and I found another way. So this requires, there is a plugin for computing signal to noise ratio. The way we did it in class is we were looking at the signal to noise ratio, if you remember, isolating a specific rectangle within one phase and a specific rectangle within another phase. So generally it requires a comparison. Okay? When you have a general image, you don't know that necessarily. So there's another way to define a signal to noise ratio. And it's as follows. Basically take your reference image, which is your original image, and take your T as a sort of a filtered or test image, and look at their differences and sum them all up, the squares of the differences, over the entire domain. Okay? And basically what the original sum up of the squares of the actual value was. And this is sometimes used as a good number. So it's what to me this is, it's like there are different definitions. So you can look at the maximum, though this is a little more sensitive to having an outlier. Okay. This is the sum of the squares of the values. Okay. And then there's different others. You can just look at the mean square error over the entire image, as well as mean absolute error. Now, all of these numbers, is there a specific number that is the number that you're going to look at? That's always difficult because the images that we look at, their actual values are scaled arbitrarily or based on whatever is common in certain area. Second part, so the values of R and T are somewhat arbitrary on some sort of scale. The second part is that we might have different types of noise. So X-ray images will come with certain type of noise. Microscopy images will have slightly different noise. All of them will have noise, but it has slightly different sources. So it's not always clear which would be the best number. But I actually ran this. So this requires, and again, I will update the slides. It requires putting a plugin. So let me just briefly review how it's done, and I will now do it for you. You can watch for now, but you can also quickly do it with me. So I think this is something useful in you evaluating what is the change you made to an image in some sort of statistical sense. Okay? What is the best way to evaluate that change is, again, open to discussion, but this is actually taken from a textbook on digital analysis. So it's one way to evaluate that change. So I'm going to show you first. This is one of the plugins. And I'll have to open it again, apparently. No, cancel. So this is you could just search for SNR plugin Imagel. Hello. So SNR plugin Imagel. Yeah. So it's actually one of the sort of official plugins that you could add to your Imagel. Oh, no, that's the wrong link. Plugins, Imagel. Apparently, that's not the link. Okay. Let's go to this after all. Control click. Biomedical Imaging Group plugin. So here it will explain to you, and this is common for a lot of plugins. Also, if you wanted to create a plugin to put into Imagel, you could follow the steps, and Imagel has quite a bit of references on that. So you download this jar file or Java file, either of them. Okay. And when you download this, you place it. So when you installed your Imagel or Fiji, there is a folder under that name, and you throw that plugin into subfolder plugins. You literally just drop it in there, and you can see that I dropped that snr_.jar right here. So do that. That's a good exercise for doing any plugin that exists for Imagel or Fiji. So when you drop that, then you restart your Fiji, and it should then show up in plugins. And here it is, SNR. Okay, did everybody drop it in your plugins, restart? So this is just a general thing you do to install a plugin. Okay, excellent. So now restart Fiji, and it should show up. So now we will open file open. There should be open recent image. Open recent, and this our unsharp sandstone called sharp sandstone. Not so sharp sandstone image. So if I open it, I will also, what is that? I don't know what I clicked on. I will create a duplicate. Actually, two of them. Okay. So now I will see what does my statistical measure SNR as defined on that slide, which is sort of measuring a distance between two images that is you can average in different ways. So I need a plus plus plus. So my second one. Okay, three of them. So now I will, on this first one, I'm going to perform median filter. It was an image filter, no, process filters. Median. Radius 1, radius 2, what do you want to do? 2? 1? Let's do 2, doesn't matter. As long as we use 2 for both, right? So here's one, that's quite a change. Okay. And then this, so let's now do SNR. I'm gonna say SNR. I'm gonna do my reference image as my original so that the reference is the same. Change this first one, and then my test will be this median filtered. Okay. I'm just going to say compute. So this signal to noise ratio is defined by this sum and sort of expressed in decibels. This can be a large number, right? So a log makes this. So it's 14, 19-ish to 20 almost. The root mean square error. So this is normalized by the number of points, okay, is about 26. And mean absolute error is about 18. Okay. Now we will do the other filter. Over here. So I'm going to okay, I'll move you out. So process filters. What did I did median, now it's mean, right? Yeah. It's quite blurry. So now I will just do the another one. So now it's going to change to and compute. So this was, luckily this will just add so I can directly compare. So I can see in terms of median absolute error, I'm larger for mean than I am for median, ever so slightly, okay? Mean is again a little larger in this root mean square error. My signal to noise ratio though is slightly smaller, but it's arguably too blurred, so I do want larger I want SNR to be larger for a sharper image. So this is, again, ever so slightly in terms of numbers, this SNR is larger, which is good. I want signal-to-noise ratio to be larger. Okay. So this is one way to put the numbers. That said, look at the image. In both cases, really, I am not happy to what was done to this image because my thin features have disappeared, and maybe that's important. So if that's what's important to you, none of these filters works well. Median works ever so slightly better because I see them a little better than I do here, but none of them is good. So look at the histogram. Don't forget to look at the image. Look at the image and see, convince yourself that the features you're interested in are not gone. And then if you're doing this over a number of methods, you need a number to compare, then these are good numbers to compare. But take everything with a little bit of, like, with a grain of salt. Look at the image, evaluate for yourself. Ultimately, later on, what we're doing later on, segmentation and then doing something with the image will ultimately confirm if your analysis, when you count something up and measure it and compare it to an experiment that you have as a verification, say porosity, okay, then you can say that after you're satisfied with that whole procedure, I would call then filtering and segmentation as satisfactory. Okay? But directly it's a little hard and it's a little relative. So there's an absolute number we can hang on to. So just remember that. Okay? Part of it is practice. Okay? I was discussing this practice with a colleague and now at University of New South Wales, Krista Farnes, who's been in this area for a while, and they at some point he graduated, I believe, from Australian National University, or that's where he worked for a while now, I don't know anymore. But they actually had, in the processing, they had 4 people who could sign off on filtering and segmentation, right? Because they've had the more practice. So they would let people, so ultimately there's a little bit of built-in into this intuition, working with the images that are coming from a specific device. You kind of learn what type of noise and how to handle it. Right? So some of it is still practice, and it's hard to come up with absolute measures. But these are some suggestions that I hope you find useful when you use them. All right. So now we will improve those filters a little. So one of the main problems that I pointed out in that image is that I'm not happy how either that median filter or mean filter, how they're handling thinner features and sort of like distinction of thinner features within my image, because they kind of smudge and smear. And smudging and smearing is very good for removing what's called like speckled noise, which is random in nature. Okay? We don't have noise that is random in nature. If you remember anything from the lecture 2 on imaging, there's this old noise that, like, I'm doing reconstruction. Even if I had random noise in the process of detection of an image, then I'm doing reconstruction and suddenly I'm correlating that noise across an area during reconstruction. Right? So the noise will be correlated. Then I have those ring artifacts that kind of make a round. One bad pixel in a detector makes a round through my image, right? So it's a correlated ultimately. So it's not random. I cannot remove, my median filter will not remove a ring artifact because of that. These median and mean filters, they're very good for like removing some random noise that is often called salt and pepper in images. And you can, if you play in image J, you can add salt and pepper. Actually, let me show you that. So sometimes you can test how your filter works by adding a noise to a known image and then looking at the differences both in the noise and So you kind of have a ground truth that you add noise to, then you filter it and see how filtering compares to the original. That's one way to see how filtering works. But that's somewhat artificial for these images because it's extremely hard to say that, we cannot say that the noise is random. But I believe in the filters, process filters, you can add noise. You can add noise, salt and pepper. Or you can try to despeckle, except that despeckling works only for salt and pepper type of noise. So let me add noise. Here's a salt and pepper. This is random points that are black and random points that are white. That would be your salt and pepper, right? So that is random noise, but that's not how noise works in imaging devices. So if I now despeckle, that's going to work really well. That's what despeckling works. Okay? And that's where median filter will also work really well because it will ignore the outlier. Right? All right.
Just following the process, adding the salt and pepper and if I were going to measure my histogram from the original image, is it changing?
So that's if you change if you basically compare the histograms, the histogram actually shouldn't change much. Shall we test that? Let's test it. Javier doesn't trust me. Let's test it. I don't know. I might bite my tongue right now. Okay, so this is my image. So take an image, original image, and let's do a histogram. I should just learn to search here. Histogram. There we go. Analyze histogram. Right, so this is my histogram. Now I'm going to add noise, salt and pepper. Okay. So I'm going to do histogram. And I will see on the histogram that I have a line here and a line there. Those are my salt and pepper. Yes? So now let's remove it. This speckle. Okay. And we can do histogram or we can subtract to the original, whatever works. But I would have to reread the original right now. So let's just do histogram. Okay, am I going to learn? Where is it? I have moved some of there was a little more zeros in the original, so I removed some of them. So it's not precisely the same, and this has ever so slightly changed. So it's a slight difference, right? I can see a slight shift in the mean, though this is not normally distributed, so, you know. But it shows you that there's a slight shift. But overall, that's a good it's pretty close. They're pretty close, the original and this add noise, this speckle. Okay. But basically, do you see how that can be used for verification of how these things work and how well they work? Add noise, remove, and then see how good it is. Or remove by different filters, so you can also see how different filters work against different types of noise. The problem is, again, with X-ray images or the like, it's a little harder to qualify the noise as just salt and pepper or random type of noise. It seems that there's even a plugin, add noise, and I'm not sure what does it. Oh, I added noise. It's an image, right? The histogram is output an image, so image J is saying, sure, I can add noise to that. Hilarious. And it's an RGB image, so I have added colored noise. Hey. Okay. Shall we do histogram of a histogram? No, just kidding. All right. Everything is an image. All right. So the basic idea is, can we somehow stay within a phase without knowing what the phase is or having not detected what individual phases are? Can we try to kind of operate with filtering without going over the edge? Okay? And mixing up the values from what a different phase is. By different phase, I mean something that has very different grayscale values. Okay? So technically, if I wanted to identify edges in an image, there where the gradient is large. So I have a large difference in values over short distance, right? What is the definition of a gradient? F of x plus delta x minus f of x, that's the difference in values, over delta x, the distance between them. So if I have short distance and large difference, I'm going to have a large gradient. Excellent. And partial derivatives work the same. Okay? Overall, as I pointed out last time, think of a gradient as a vector pointing in the direction of the largest change. In the positive direction, in the negative, the smallest. Okay? So a lot of numerical methods. So for instance, in optimization, you will have, everybody has heard about conjugate gradients method in optimization, finding minima and maxima. You want to find them fastest, so you're going to go against the direction of the gradient, right? Because that's where your largest change is. And if you're looking for something that has, so you're looking for, on a function, you're looking for a minimum. Your optimization is looking for a minimum of some sort. And you're defining your problem as finding a minimum. Minimum is that where the gradient is 0, your f prime of x is 0, right? So you're going to, in multiple dimensions, you want to find that where your gradient is 0, right? And you want to go, if you think about a valley and there's a lot of hills around that valley, you want to slide down the, the steepest hill, okay? Fastest, right? That would be your fastest way to minimum. Yeah, so a lot of methods or numerical methods are exploiting that fact that gradient is pointing, positive gradient is in the largest change, and negative is the other way. Excellent. So I would like to smooth the data set along an edge of this large change and do minimal smoothing across an edge where I have a sharp change. Okay? And that can be expressed as gradient. So that's basically at the heart of a method called anisotropic diffusion. So it finds basically the direction of least change and smooths primarily along that direction and tries to do that iteratively. The problem is, how much do I iterate? So these are the original paper is Perona and Malik. And good news is it's already implemented. So we're going to do our not so sharp sandstone. Open it up. And we're going to try smoothing. So I want you first to play. The problem with all numerical methods is that they have certain parameters that you need to define. There's diffusion parameter along the minimal variation, diffusion limiter along the maximum. There are some suggestions here. And then how many times you do it. All of those will affect how much you're going to actually smooth and smear your image. And unfortunately, I cannot clearly tell you when to stop. That's something that you have to play with. And you have to remember to look at the histogram and look at the images. Just because histogram looks better doesn't mean that the image is actually where you want it to be. So try to play with it. I'm going to play too without looking at my slides. What do we really mean by this time step? I think that's really, so number of iterations. So there is actually, let's play with it. I don't right now, and I don't think I have it in my slides. Don't save. Let me close up some of these. I'm gonna leave this. This might be useful. This is not my original anymore, so I'm gonna open it again. It's my median filter. Don't save. Median. No, this is median and mean. I'm gonna close my median and mean. I'm gonna leave this change just to kind of compare. I'm gonna reopen. Okay. And my original, and then I'm gonna duplicate. Okay. I'm improving. I learned to duplicate. It's one of the plugins. Okay. I'm going to show filter statistics just for kicks. I'm going to do one time step just to test it. Again, this diffusion is dt. You're ultimately working with the partial differential equation. Sort of diffusion dt, right? But it's a time step, which is fictitious time step because there's no diffusion process here, right? Oops. So this has not changed much, so I can go a little further. And let's see, for statistical purposes, so I said, hey, let's go 20 time steps like this. And it's keeping things every 20 iterations. That's what I'm asking it to do. Process anisotropic diffusion. Okay. So if I go 20 time steps, that's the only thing. Then I'm smoothed much, much more. Okay. So it's smoothed here within, but I am keeping these crevices here pretty clear. One of them has semi-closed here. Okay, so maybe I went a little too far. Okay. But I can only judge by looking at the features I'm interested in. If you look at the histogram, so I would say I went too far because I'm inherently interested in keeping fractures in there. So let's do histogram. You see how much sharper it is. Okay. So I have definitely defined my phases better by this, by removing some of the noise. Okay. Compare. So basically I have now two sort of clear phases within what was all smudged together, at least on the histogram. What are those? They're in these gray values, so it appears that I have clearly defined this is a phase, and a little darker, and this one. Okay. Some sort of microporous something, or maybe it's full of clay. Who knows what was in there? Okay. So now that seems to have appeared as a, no, wait, the majority of stuff is this, so that's that. This phase might be this. So these greens possibly have slightly different mineral composition. Yeah? So I am happier here compared to the median filter. I'm happier with how is this type of smoothing. I would just say that this is went slightly too far, so I would probably do less number of steps. So here's the raw image, 20 iterations, which is a bit much, 5 iterations, maybe a little better, but I'm keeping the variation here, okay? And you can see the histogram that has much sharper peaks. Here they're overlaid. Okay. Shall we now do, just for kicks, let's do that SNR. Plugins. Okay. And what is this one called? Iteration 20. There we go. Compute. So my signal to noise ratio has definitely improved, so I can identify things better. Overall error is also not that big because I didn't go across the edges to smear things. Okay. So this overall performs better, but you still have to play with it to see when to stop. And actually looking at the papers now, I said I'm forgetting how are these A1 and A2 in different directions. This is a vector that goes in the direction of the gradient and against the gradient, a direction of the gradient and orthogonal to it. So there are two coefficients that you can vary, but seeing the equation can give you a little bit more intuition on when to stop. But with different images that you have will work differently because your gray values are slightly different in each image that you process. Okay? Now you could basically, if we went for 100 iterations, the histogram would look great. You can try it out. But the image itself is losing its original features. Let's try. Plugins. Let's go number of iterations 100. Okay. And well, don't keep them, just keep after 100. Okay. Oh. Ah. These are so small. I'd say that's a little too smoothed, right? And I have started to close in this opening, which might be problematic depending on what I'm trying to do. But again, you're the judge. This is kind of almost artificial. It's like, this is not an X-ray image. Right? Okay. Questions? There's no one thing that will, one hammer that will be good for every nail. Work with multiple filters. Always look at the histogram, always look at the image. You can also look at the general statistical difference between the images. And those SNR and median square error tools are pretty good. especially when you have to compare more than two things. Right. So let's introduce. So this is filtering. Again, a general note is that this pure uncorrelated noise is easy to remove, but that's not what typically travels with X-ray images or any kind of other imaging. Okay. So when you have beam hardening ring artifacts, they're heavily correlated, and that's the despeckling is not going to remove. Okay. You can also add control noise, and this is just a note for you to do it. But again, that noise is sort of artificial and it's not realistic. Okay. Now, I'm going to also shortly, so one more, and I'm going to deal with. There's one more non-local denoising filter that is trying to, it's a little more computationally involved, but it's trying to find similar regions throughout the image. So not just locally. All of these filters that I have introduced, they're working on like one local region. Like there's that filter with the compact support, if you will, and you're just working locally. But they're trying to compare across the image what those differences might be. And one of the best methods along those lines is called non-local denoising. I'm going to give that as a homework, sort of to compare different denoising algorithms, because we have to install it separately. So I'm going to assign that as a homework and give you pointers how to install and try it out. So now we will just move on to basically something that is related to filtering, and that is called image registration. So in essence, if I was doing the same, let's say that I have two images of feature, and I'm trying to say that this is an image that has a whole lot of spheres in there. And I have a filter. Yeah. Actually, I have one. Look at that. Okay. So let's say that I have sphere. And I have an image that is a whole bunch of. This is very easy in biology. They actually look at cells that are kind of spherical. Well, let's say we have foam, okay? So we have foam, order motion. So imagine that convolution or cross-correlation process. If I move this around my image, I would get where I actually have a similar identical circle, I would get a large number for cross-correlation. Because my numbers would simply, let's say that these are actually, so in a very simple way, these are all 1, and around it is a 0. Very simple image. Okay. So as I move around, as I basically center above the circle, I'm going to have a pretty large cross correlation. Right? If they're not so well registered, we use word registered, then correlation is a little less. Okay? Largeness. So basically, one way is like you give yourself another image, and that can be a filter, another image, you name it. Okay? And as you move it around, you should get a pretty good large value of cross-correlation or convolution, either way, where they kind of align. Yes? So that's one way to actually find. Sometimes I'm actually looking for a feature, and I'm trying to find it in a larger image. And I have some sort of description of that feature, which is also an image. I could also have images at two different time steps. If you remember particle velocimetry, right? I have a moving particle. So if I cross-correlate two different time steps, I will actually see where the particle has moved. Okay? So you can actually figure out the shifts that you have in the image. So the cross-correlation often tells us how things have shifted or where things are, which we call registration. And that's why it kind of gets covered under filtering, because we use the similar type of filters to actually find things. I will merge this, but I have it in a slightly separate PowerPoint, which I'm gonna put in. And I was okay. So I was working with technically you could just do an image. This is one of those circular models. That was a simple way for me to draw a circle. And you can do correlation of an image with itself. So you take an image. This could be just as large, right, as this thing is. And I could, so let's say that I have one of these circles and they're the same size. I can correlate image with itself. And if you did that, then there's a MATLAB code that will do both correlation, which is just XCore, and cross autocorrelation, which is if you just do a single input, it's going to do autocorrelation. If you give it two inputs, it's going to do cross correlation. So you can play with that. This is where I actually like typing things in. I didn't. Well, I need to search in ImageJ, but this was more intuitive to me to do. And basically, we can see how as I'm moving around circle over the same circle, the best hit I get when I completely align them. That's this value here. So I have registered image with itself. Right? If I move them a little away, I'm not going to go, I'm going to get some overlap. I'm going to essentially measure in the 0 and 1 world, I'm going to essentially measure how many of them overlap. Right? So I'm going to move away, I'm going to actually see a little less overlap. And as these circles don't overlap at all, so I move this entire thing like this way, right? This is my only overlap. Of course, I have to fill in a whole lot of values here. Then I'm going to get a 0. Yes? So this is just to give you a little bit of intuition about how this correlation works. But that's how I can actually find objects in an image. In porous media, cross correlation, like once you actually make this a full image of circle, even if they're circles, cross correlation becomes a little difficult. But just understand that basically cross correlation gives you a way to register things to each other, if you can, or as little as you can. Okay. And there is, I'm going to put these couple of slides into our base and update the main slides for filter. All right. So back to registration. No. I might want to register different things. Sometimes you will actually have actual motion that you try to register, and this is better understood if you actually have objects like hearts. So if I had medical images and my heart is moving and changing, I can measure the amount of deformation by trying to register the moved heart with the original. So that is a great value in medical imaging. But also, we also have sometimes in porous media, we have done images that are done at different time steps with different, I might actually have everything in the same position, but I have fluids that have changed in the pore spaces. So I can try to register. So we are gonna show some examples of that. So sometimes before and after some sort of chemical alteration, I might want to register things in the same position, especially if it hasn't been. Or I might have different modalities. So let's say that I have a sandstone imaging. This is often done to improve identification of mineral components. Let's say that I have a sandstone core. I could do an SCM of the top or somewhere in the middle and compare that SCM and try to find it in my large image through cross sections. And basically I will do that by attempting to register. They just have to be with the similar sizes or on the same physical scale. So here's an example where we had, this was CO2 dissolution, and this was 3D image to a 3D registration. So cross correlation in 3D, it's heavy. So if I did this entire process, and I was actually working with boxes over boxes, and then moving over, so you gotta do this one image with centered in every pixel. That's a lot to compute. Now if you do that in 3D and do it with every voxel, box over every voxel, you can see how that computation is a lot. So that's something that is intense. But here you can actually see how as the core was dissolving, they were trying to find the biggest overlap of what was not dissolved, right, with the original. So basically you can see where the original phase was. So this is basically the most dissolved. So it dissolved a lot from the outside. So this is the original dissolution state 1, dissolution state 2. But that was imaged at 3 different time instances, so you can register the two to find, because then you will see who dissolved, right? So now I know this region dissolved by the time I reached the green stage. Yes?
As a clarification, so they run 3 scans for the 2 different stages, and then they use the other 2 stages to register on the region.
Yeah. So I registered this changed with the, so I did a correlation of the changed with the original, right? And when you have the maximum overlap, you know that that's, possibly you had something also happen. Sometimes you have rotation to the core, or you have literally moved the core and put it back into the X-ray scanner. Now you are in the X-ray scanner. Can you guarantee that you're going to put the core precisely in the same spot down to 5 microns? Right? So registration can help with that. Right? So even if you moved it slightly, that's going to cause offset, and it's going to be harder for you to calculate later what has happened in the precise location in time. And in order to do that, you might need to align them or register them. Does that make sense? So even small shifts, sometimes those shifts are simply because, let's say that you have a setup. As you're rotating in the X-ray, we've been in the X-ray, there's a rotation happening, right? And you're counting on that plate to mechanically rotate back precisely to the same position after it has done a full circle, right? Well, it does that with a certain precision. It's a mechanical device. It's not necessarily perfect. Now, let's say that we have figured that out and it does that. If you also have some sort of process happening, let's say that you have a pump pumping in fluids. We're pumping in fluids in pretty high pressures. Those fluids will move the core, especially when the core is this small. Right? You're going to have an impact on that, no matter what you do. So the registration might be helpful just to basically align things back to the way they were originally positioned. And then you might just physically, a student of mine, Hassan Khan, some of you maybe know him. he graduated last year, he was actually physically moving the core to the lab, doing the experiment and moving it back. So that could, now he was actually just reporting saturations per slice and averaging things, so he avoided. But if he actually wanted to go to align precisely what happened, right, for different stages, because he was doing his experiment outside of the X-ray scanner and then moving it back for scanning. Right?
But how do you account for the different CT number if it changes throughout the duration of
the correlation? So it's still relative. So sure, maybe your range coming back because of the different X-ray energy used or something.
Yes. For example, I was an experiment on hydrates. As you know, with time, this experiment lasts like 2 weeks.
Mm-hmm.
So, and I was doing a scanner every day, just trying to see how my hydrate system was evolving.
Mm-hmm.
But even when I was using the same energy, the same sets and everything, because of if I compare each time, I was getting different values because of for this, even for the same components, even for the insulation material, I was getting like different CT numbers.
Technically, let's say that I'm correlating this with itself. It's just instead of 0 and 1, I have 0 and 2. So my 1 has changed to 2 in my second setting, right? The correlation will still be the largest. That basically just overlaying and summing over your existence of hydrate is still like there by certain larger value. I don't know whether they were larger or smaller in your image, right?
Yeah, because there's some point when it's very hard to distinguish between the hydrate and the methane. There is still like around the system. So that was one of the challenges that I had when I was doing my segmentation.
That's still a problem of contrast. But if you were trying to align things, okay, then I would still say alignment would be if this image is 0, 1 versus image 0, 2 on the second go, right? You would still have the best alignment once they're on top of each other, right? In terms of just having the highest correlation in that spot. Now, your problem, you might want to look at the differences still. Even if the X-ray numbers or CT numbers are changing ever so slightly, the differences with respect to the original image, once registered, might be helpful in distinguishing the phases. So if you have multiple changes and things are changing in the image, differences are more telling than the absolute differences. And that's common in X-ray. So you you're kind of playing within the same set of values. So you initially had a very good contrast between two phases you had in there, and you introduce the third phase that is somewhere in between. You're going to blur the contrast between two. Like pairwise, you might not have as good of a contrast anymore. So that contrast will show up better if you're looking at the differences between the original images. I think this is where I'm going to stop for today. Let me just see what the next image is. So in movie industry, what you can do is you will compensate for motion when you have specifically if you have camera moving while you're doing the movie set, like you have camera that is moving on that, whatever is the name of the device where camera slides when they're shooting a movie. So you have to often compensate for that movement, right? And possibly, but what they have there is that they can take a lot of images and more frames per second, and basically because of those correlations they can compensate and sharpen the images as a result. We don't necessarily always have that in X-ray imaging, but that's something, the same type of approaches could be used to enhance force media imaging as well. There is registration software This is somewhat outdated, so I have to say that like this is from 2-3 years ago. There was not much on registration that was very good, other than just like software that calculates cross correlation, right? So I actually probably have to redo this search and see whether some plugins, magical plugins, have reappeared in the meantime. For instance, the non-local means denoising has appeared only in 2016 or 2017 or something like that. So relatively recent. So things are rapidly evolving in this world. Okay, I'm going to stop here for today. I'm going to update this